Hey everybody, in this video I'm going to talk about projectile motion, which is a very important example of two-dimensional motion under constant acceleration. So the basic picture for projectile motion is an object being fired or shot off the ground with some initial velocity v0, and the only thing that's acting on the object is the force of gravity. There's no air resistance and there's no drag. We can actually consider those things pretty easily, but normally we won't consider them when we talk about projectile motion. So this object is clearly going to move in both the x and y directions, the vertical and the horizontal direction. So I'm going to start by writing down the two-dimensional kinematic equations of motion for constant acceleration. There we are. The next step in the solution process is to identify some of these variables. We already have the initial velocity right here, which we're going to have to put into x and y form. So let's just be clear about that. If that's given to us, we certainly know the initial velocity in the x and y direction. Here we have the x and y position initially, so we can identify that with that exact location right there. And we're also going to want to find out what the acceleration is here and here in the x and y directions. Well, unlike this setup, we may or may not be given the initial position, initial velocities, but the acceleration has to come from Newton's second law. That's the only way we ever learn the acceleration of a system. So we're going to have to solve Newton's second law for projectile motion. Luckily, that's not too difficult. So here's the free body diagram for an object in projectile motion. There is only one force acting on the object. It's gravity, and gravity is always pointed downwards. I want to solve Newton's second law, so I better get a coordinate system on here. I'm just going to pick x, y. That matches the x and y that I picked over here. And the next step is to just write down Newton's second law. Remember that in Newton's second law, the force here and the acceleration here are vectors. That's important for this case because we know there's going to be some kind of two-dimensional motion going on. So we have the sum of the forces in the x direction is mass times acceleration in the x direction, and the same for the y direction. So let's sum up all the forces in the x direction. Okay, there's no forces in the x direction. So that part of Newton's second law simply tells us 0, that's the left side. The right side is always max, and so that simply tells us that there is no acceleration in the x direction, and actually we can just drop those terms in the kinematic equations because the acceleration is 0. If we want to solve Newton's second law in the y direction, we have to find all the forces in the y direction. There is only one of them, Fg, and I put a negative sign in there because the gravitational force is pointed downwards. Fg is negative m. G. That's the left side of Newton's second law. The right side is may. If I solve this, I get that ay equals negative g. If you remember, this is the exact same thing we found for free fall, except for free fall we are explicitly only moving in the y direction. Now we're moving in the x direction as well. But what we can do is we can rewrite the kinematic equations and set ay equal to negative g. And in this rewriting, I've also dropped out the acceleration, so we have a simplified set of equations in the x direction and a slightly simplified set of equations in the y direction, just with this g right there. So let's talk a little bit about the simplification that I did in the x direction. This equation now becomes quite simple. It simply tells us that the velocity in the x direction as a function of time is the constant initial velocity in the x direction. So whatever the initial velocity was in the x direction at the beginning will be the same for all time, no matter what time I pick. So let me just try to draw that a little bit on my diagram. So I've explicitly broken the velocity into x and y components, so you can see that this equation means that this component of the velocity will be exactly the same no matter how long this projectile is in motion. So that means as the object moves in its path, as it gets right here for instance, the velocity in the x direction at that point will be exactly the same as it was initially. We can write vx naught because it will be exactly the same. The velocity in the y direction will be described by this equation. So specifically the velocity in the y direction as a function of time starts at this constant value when t is 0, but as t gets bigger and bigger, it will contribute a negative g times t to this equation. So specifically, this thing will start out here as a positive value because it's pointed upwards, but it will get smaller and smaller and possibly go negative as t gets bigger and bigger. So we can draw that just by saying, okay, after this first little chunk of time, the velocity in the y direction is a little bit smaller. And that means that the velocity is right there, and our object moves to that point right there. And we can continue to play this game to sort of map out the path of the object. And we see that we get exactly what we would expect, an object that looks like it's undergoing projectile motion by moving in some kind of parabolic kind of path. Okay, so at this stage, we're again at the point of being able to solve a large number of problems given the equations. Here, I'm just going to write them again. These are the final equations we have for projectile motion. They are true for any object which is only undergoing the influence of gravity and has some initial position and initial velocity. Solving these equations is just like solving any other kinematic motion problem. Count your knowns, count your unknowns, form an algebraic solution, and make sure you understand what the problem is asking for. Okay, well, this has been an introduction to projectile motion. Thank you everyone for watching.